Cool. Yeah. So, hello, everyone. Welcome Biomed Colloquium. I have the great pleasure of introducing Professor Martin Nowak as today's Biomed Colloquium speaker. He got his PhD in biochemistry and mathematics at University of Vienna. And then Dr. Nowak worked at the Oxford with Sir Robert May as an Erwin Schrödinger postdoctoral scholar. And then he conducted research at the Institute for Advanced Study at Princeton. And there, actually, he established a program for theoretical biology. And then early 2000, Nowak became a professor at Harvard University of Mathematics and Biology. So he has working on mathematical description of evolutionary process, including the evolution of cooperation and human language and dynamics of the virus infection. And he is also the author of that famous book, Super Cooperators. So I strongly recommend you to read his book. And the topic of his talk today is very attractive, the evolution of cooperations. So please join me in welcoming Professor Martin Nowak.
Thank you. Thank you for inviting me to give a talk. I have very beautiful memories of visiting Korea. I think I was there at the Seoul Digital Forum. It was maybe 2012 or 2013, and it was a wonderful week that I spent in Korea. I have also worked with Professor H.G. Chung. He visited me and he spent some time in my group. But I also had a graduate student, actually, Wan Gang, and he was at Harvard University and he's now back in Korea. So I have ties with Korea. It's very nice for me to be back. So the topic of my talk is evolution of cooperation. And cooperation is a phenomenon that has been around for a very long time. And it is, in my opinion, a fundamental principle of evolution. And here I have 3 examples of cooperation. These are cyanobacteria. And the cyanobacteria form filaments. And every so often a cell dies in order to feed the others with nitrogen. So a cell dies in order to help others reproduce. This is kind of cooperation as was in existence more than 3 billion years ago already. This is social insects, ants. The workers do not reproduce themselves, but they help the queen reproduce. The eggs are laid by the queen, the workers help the queen reproduce. This evolved 125 million years ago. And then cooperation is a very important feature of human society. We help one another. Here is painting of Vincent van Gogh of the Good Samaritan. And people help one another. But I will argue in my talk, what we need now is global cooperation. And without global cooperation, intelligent life on Earth is not stable. I think it's a very critical moment for human species, and human species needs to achieve global cooperation unless it generates instability that will undermine its own survival. So this is a timeline of the events that happened. Big events. So the universe is 13.8 billion years old. The Earth is 4.6 billion years old. Then maybe 4 billion years we have an origin of life on Earth, approximately. By 3.5 billion years we have prokarya. And by 1.8 billion years eukarya. By 600 million years complex multicellularity. And then most recently human language. And these are the main events of life on Earth. And my argument is that cooperation is the master architect of evolution, that cooperation is involved whenever evolution makes great new discovery. So we ask the question, what is it that evolves? What is the carrier of the evolutionary process? And Ernst Mayr, a famous biologist at Harvard University, pointed out the carrier of the evolutionary process is population. Only populations evolve. And populations consist of individuals of reproducing, is a collection of reproducing individuals. And then in population, we have mutation. Mutation means the different type emerges. And then we have selection. Selection means over time, one type might reproduce faster than another type. And these are the two classically fundamental principles of evolution, mutation and selection. And I think that third fundamental principle of evolution is cooperation. And cooperation is whenever cells help one another. And these cells that help one another might form an aggregate, and this aggregate is now higher level of organization. So cooperation is master architect of evolution, and cooperation leads to higher levels of biological organization. And examples would be, I have done theory on pre-life. This is mathematical description before origin of life. But then protocell. Protocell is cooperation between lipids and RNA. Cells, we have different parts of cells cooperating. Genomes is cooperation of genes. Cellular organelles cooperate in eukaryotic cells. Multicellularity is cooperation among cells. Animal societies cooperate, and human language is a consequence of cooperation. So in my opinion, cooperation is master architect of evolution. What is cooperation? There is a donor, and the donor pays a cost, and the recipient gets a benefit. It's an interaction between an individual, a cell or a person, and cost for the donor implies benefit for the recipient. And this leads to the prisoner's dilemma, or the so-called donation game. And the payoff matrix of this game is, if you cooperate and I cooperate, you get B minus C, because you have the cost for your cooperation, but you have the benefit of my cooperation. So your payoff B minus C. But if I defect, then your payoff is minus C. You have cost for your cooperation, but no benefit. If you defect and I cooperate, you have only benefit, no cost. And if I defect and you defect, you get 0. So the rule of the game is B greater than C is greater than 0. And what would you do? How would you analyze this game? If you don't know what I will do, let's assume I cooperate. If you assume I will cooperate, you have a choice between B and B minus C. B is greater than B minus C.
Yes.
If I cooperate, you defect. If I defect, 0 is greater than minus C.
Yeah.
If I defect, you also defect. No matter what I do, you should choose defect.
Yes.
And I will defect, and then we have 0 payoff. And this is Nash equilibrium. But we are very unhappy because B minus C is greater than 0 would have been better payoff. Cooperation is better, but not Nash equilibrium. So what is the dilemma? Do rational players defect and end up with a low payoff 0? Do irrational players might cooperate and receive a higher payoff B minus C? Rational means to analyze Nash equilibrium and understand Nash equilibrium. And here, in order to analyze this, we can use game theory, as was invented by John von Neumann and Oskar Morgenstern in collaborating in Princeton after Second World War. And it was then further developed into biological game theory, evolutionary game theory by John Maynard Smith in Britain, but also by my PhD advisor, Carl Sigmund in Vienna, who wrote important book, Hofbauer Sigmund on evolutionary game theory. And Carl Sigmund was my PhD advisor in Vienna. And I met John Maynard Smith when I was in Oxford. And I had great interaction with him and learned very much from John Maynard Smith. So now I have given analysis in terms of rationality, but I can also give analysis in terms of natural selection. And in natural selection, we can say mixed population. They can be cells, you know, they have no cognitive capacity, no reasoning, you know, they're just cooperators and just defector. And whenever they meet, defector have a higher payoff. Because this defector gets from that cooperator a higher payoff than this cooperator gets from that cooperator. So no matter what, cooperator defector has higher payoff. If higher payoff means reproduction, then after some time more defectors, and in the end only defectors. So in any mixed population, defectors have a higher payoff than cooperators. Natural selection opposes cooperation. So natural selection needs help to favor cooperators over defectors. And help is given in 5 mechanisms. So there are many thousands of papers written on how to get cooperation. And in 2006, I proposed they can be classified into 5 mechanisms. And these mechanisms are direct reciprocity, indirect reciprocity, spatial selection, group selection, and kin selection. And I will mostly talk about direct and indirect reciprocity. I will briefly mention spatial selection, but mostly the first 2, because they are the most relevant for humans. So direct reciprocity is I help you and you help me. So we have repeated interaction. So you have invited me here, and now next move, I invite you to visit me. And then you can invite me. So I help you, you help me. So this brings to repeated prisoner's dilemma game. In repeated prisoner's dilemma game, there are 2 players, player 1, player 2, and now there is a sequence of moves. And now it is no longer the only Nash equilibrium, always defect, is no longer the only Nash equilibrium. There exists the Fock theorem that says other equilibria are possible. But the question is how to play the game. And there was a computer tournament was organized by Robert Axelrod, and he said send strategies and computer programs will play against each other. And he received strategies, they played against each other, and the simplest strategy won the game. Simple strategy was a computer program of 3 lines, and it was submitted by a Russian-Canadian game theorist Anatol Rapoport. And 3-line program was tit for tat. I start with cooperation. If you cooperate, I will cooperate. If you defect, I will defect. So tit for tat starts with cooperation, and then it does whatever you did last round. And this was winning strategy in Axelrod's tournament. And tournament was repeated, and more strategies were submitted, and tit for tat won again. It was winning strategy in 2 tournaments. When I started to do my PhD thesis with Carl Sigmund in Vienna, it was world champion. Tit for tat was world champion of repeated prisoner's dilemma. But problem of tit for tat is errors. If errors occur, then cooperation disappears. So in my PhD thesis, I proposed generous tit for tat. Generous tit for tat is I start with cooperation. If you cooperate, I will cooperate. And if you defect, I will still cooperate with a certain probability. And this probability needs to be calculated. It depends on cost and benefit. And this was in my analysis of evolution. If we use evolutionary analysis of world with errors, it was the winning strategy. So natural selection leads to forgiveness because we can forgive defection. And later we found another strategy, which is called win, stay, lose, shift. If I'm doing well, and doing well is one of the 2 higher payoffs, B or B minus C, then I will repeat my move. And if I'm doing badly, then I will change my move. And this strategy also gives rise to stable cooperation. It can also correct mistakes. It can deal with errors. And it is more stable with respect to neutral drift to unconditional cooperation. So experts in repeated game actually know that this strategy and not tit for tat is a stable strategy. But cooperation is never fully stable. In any evolutionary analysis, there are always cycles. So you get some cooperative society, then cooperation fails, then you have defection, then you have to rebuild cooperation. It's always going in cycles. And next, I want to talk about indirect reciprocity. Indirect reciprocity is now I help you, but somebody helps me. So maybe here in this painting, the Good Samaritan does not help because he thinks first round of repeated prisoner's dilemma. He thinks I should help. A very famous example of indirect reciprocity is New York subway hero. This man was waiting for subway to come and with his daughters on the way to school, when another man had seizure and fell on the track in front of the train. And the train was coming into the subway, and he jumped down to get him up, but was too late and he could not get him up. So he pushed him down and put himself over it, and the train passed over both of them, and both of them survived.
Wow.
And he was hero, New York subway hero. But very interesting, all humans, not all humans are heroes, but all humans want to help. Humans have a very strong instinct to help. We want to help even stranger. And we have to ask, why is this the case? So indirect reciprocity works via reputation. And the idea is that A helps B, and then the reputation of A increases. Or A does not help B, and the reputation of A decreases. So if I cooperate, I have a cost and you have a benefit, but my reputation goes up. If I defect, no cost, no benefit, but my reputation goes down.
I see.
And experimental confirmation was published after our paper by Klaus Wedekind and Manfred Milinski, that in experimental situation, people help those who help others, and helpful people have a higher payoff in the end. Games of indirect reciprocity use social intelligence and human language, because people observe each other and interpret what interaction is going on between other people. And then people talk to each other about others. Indirect reciprocity reputation has to spread with human language. In my opinion, indirect reciprocity is a selection pressure for evolution of human language. My friend David Haig in Harvard said, for direct reciprocity, you need a face. For indirect reciprocity, you need a name. So for indirect reciprocity, name is associated with reputation of a person. And only humans have language, and only humans have name. And therefore, full-blown indirect reciprocity might be very particular for human society. But open problem for indirect reciprocity is that the social norms that are being used can be very complicated, and they are vulnerable to noise and private information. So for many years of research on indirect reciprocity, these social norms are like this. Basically, they lead to the question, does helping a bad person make you bad? It's very problematic. If somebody has bad reputation and you help, you cooperate with somebody who has bad reputation, are you bad? Or is refusing to help a bad person, does this make you good? I think these are very problematic, very problematic. And these are the complex social norms that are normally studied with indirect reciprocity. And I always wanted to promote simple norm. Simple norm is cooperation is good, defection is bad. And in recent approach, we found unified framework for direct and indirect reciprocity. And in this, we find very simple norm that I will actually present. So in direct reciprocity, my behavior depends on what you have done to me. Indirect reciprocity, my behavior also depends on what you have done to others. Let us now find mathematical formalism that brings direct and indirect reciprocity together. These fields are very different. So there are many thousands of papers in direct reciprocity and maybe 1,000 papers on indirect reciprocity, very different mathematics. So there was not unification. We tried unification here. So let us try unification in simple way. Imagine 4 players. First move, player 1 cooperates with player 2. Second move, player 1 cooperates with player 3. And last move, player 1 defects with this player here. And now, next question is, what should 3 do to 1? Next move, 3 interacts with 1. So if only this information is used, is direct reciprocity. But if also this information is used, is indirect reciprocity. So we want to have an equation to take care of this. And this is an equation that unifies direct and indirect reciprocity. And the terms are the following. So this is probability that I would cooperate, that I cooperates with player J. So Xij is probability that player I cooperates with player J in that equation. Xij prime is the same probability in the next round. So it's difference equation which updates the probability that I would cooperate with J if called for action. And then Wj is the probability that J acts in this round. So in that round where we update, J is actually acting and therefore observed by others. So 1 minus Wj is J is not acting. If J is not acting, then Xij is the same. It does not change. It can only change if J is called for an action.
Right.
Then this can update. And now there is a term Wjk is the probability that J interacts with player K and we sum over all K.
See.
And now we have the probability that player I pays attention to J versus K. This is a tensor, very funny. So interaction J with K, probability that I pays attention. And this here is the reactive response that strategy I has when he sees J interacting with K. So this could be if cooperation, I cooperate. If defect, I defect, for example, or probabilistic. And that is the equation. And in that equation, we can study both direct and indirect reciprocity. And this is what we get. If we have an expected number of rounds that is very large, we can get direct and indirect reciprocity to work. Many rounds. So therefore, many rounds between the same pair. But if the errors for indirect reciprocity are very high, then only direct reciprocity can work. If errors are low, direct and indirect reciprocity. But if expected number of rounds is low, only indirect reciprocity can work. And here, neither direct nor indirect reciprocity works. So no cooperative Nash equilibrium. So this is too few rounds and too high error for indirect observation. So this is region only indirect, only direct, direct and indirect, both. And biggest surprise is that very simple strategy is actually stable, and strategy is called generous scoring. Always cooperate with someone who has good reputation, sometimes cooperate with someone who has bad reputation. Same as generous did for that. Very surprising, because we knew generous did for that very well, but we never discovered equivalent in indirect reciprocity before 2021. So this was waiting for 20 years, actually. So this generous scoring is good, promising strategy for indirect reciprocity, and very simple, very simple. And it is same it needs probability to cooperate with someone who has bad reputation, and this probability, in order to be stable, depends on cost-benefit ratio. Now, next question I want to ask: can indirect reciprocity stabilize global cooperation? The problem I mentioned in the beginning is global cooperation. Can indirect reciprocity help us, for example, to reduce environmental pollution? So the idea here is that there is a population of players, and each can do something good or bad for the globe. So this drive very efficient Korean car, electric Korean car is cooperator. Very bad American car is defector. So then afterwards, cooperator or defector between people. So here, for example, defect with the environment, buys very bad car, and then other people defect with him.
I see.
But this is the game that we study here. So it is indirect reciprocity, but as also the global situation. Good?
Yeah, I will mute other people. Yeah, it should be okay.
And then this was an experimental game we performed in 2016. So we have large public good game. Public good game is where everybody can contribute for the public good, either cooperate or defect. Public good game is N-person prisoner's dilemma, and cooperation is very difficult to achieve. Very difficult. But we have here public good game, and here we have pairwise cooperative interaction. Afterwards, pairwise interaction. And so then here, two different situations, control and treatment. This is, we play this game, afterwards we play this game, but no information about what happened in the public game. So afterwards, with your neighbor, you can cooperate or defect. You remember what happened last time, but you have no information what your neighbor did for the global environment. Other situation, you do know what the neighbor did. So here you observe that this person has contributed 18 units, this person has contributed 0 units, 20 units, and afterwards you ask, do you want to cooperate or defect? So we know what our friends are doing, or we do not know what our friends are doing in the global game. And this is, if we do know what the friends are doing, then the cooperation, global cooperation is maintained. And if we do not know, global cooperation declines as standard public good game. So global cooperation is maintained because people cooperate with those who cooperate globally. It's a hopeful result. But one more question is needed in order to, yeah, so before I go there, before I go to the last part of the talk, I said that other mechanism is spatial selection, and spatial selection is that cooperators and defectors can form clusters. And that leads to games on graphs, and this is also evolutionary graph theory, and many papers are there. And the idea here would be that you cooperate with your friends. And if you cooperate with your friends, this can be a stable cluster that survives against defectors. And so on social network, cooperation can win over defection. But last part of my talk is now cooperation with the future, because we want to ask, is it possible to have cooperation with next generation, with subsequent generation? So now it is time when it is a critical situation for the global environment, and now we should cooperate so future generations have a healthy environment. And if we defect, then future generation have unhealthy environment and global warming and disaster. So we wanted to play a game. And game is the following. We did it, so we say five people, and there are 100 units in the pot. Each person can take between 0 and 20. So 5 people can choose 0 to 20. If everybody takes $20, then 0 is left here and they go home with $20. If everybody takes 0, then 100 stays. They can choose any number between 0 and 20. But now we are telling them, after you play is the next generation. Next 5 other people want to play, and they have to play with the same pot here. And the rule of the game is the following. If you leave 50 in the pot, we will replenish. If you extract more than 50, we will exhaust. So you have 100 here. If each person chooses 10, 50 left, and we will go back to 100, and next generation can play. If you take more than 50, the game is over and they cannot play. They get 0 payoff. Is rule of the game. So we tell them, you are first generation, but after you, second generation, next generation, and so on. This is explained to them. So there are 5 people lined up to play the game. 5 people will come here, 5 people will come here, 5 people will come here. If you destroy it here, you destroy it for all of them. And so we first played with students of Harvard Business School. And what do you think was the outcome? 80% of bulls destroyed in the first round. All bulls destroyed in 3 rounds.
Okay.
So then we had typical outcome was one person takes 8, cautious, 9, cautious, 10, fair, and 20, defector. So 43 is left, is less than 50, everything is destroyed, game is over. We ask people, why did you do that? Why did you do that? And people then said, because if I don't do it, somebody else will do it. And then I lose out. And then we had one variation of this game, median voting. median voting. And this is, we harness the power of democracy. So each person can say how much should be taken out, and the median is then given to everybody.
Wow.
So they can vote 8, 9, 10, 11, 20, median 10 is given to everybody.
Okay.
And if it is with voting, we have a situation that almost all pools sustained indefinitely.
I
So
see.
democratic voting is actually, it's called, comment on our article published in Nature was carrying majority secures the future. It is still open question why people vote altruistically. It is still altruistic vote. There's no theory for it, just an observation. The vote is altruistic, but it works in this. And then we had one final treatment of this game, and we called it Kyoto Protocol. There are three people who have binding vote, and 2 people, they do not sign, they can do whatever they want. So this is US and Canada. And it destroys also. And the important thing for human species to realize is that this is history of life on Earth. These are the big ages of unfolding life, 4.567 billion years ago, 4 billion years ago, 2.5 billion years ago. This is expanding the last 541 million years. But we, human species, we are just here. We are in this very, very moment. And the question is really for how long? Because what is the stability of intelligent life on Earth? That is, I think, the question, fundamental question. And for the stability of intelligent life on Earth, we need global cooperation, and we need cooperation with the future.
I see.
And these are, as a list of people with whom I have worked over many years. We have also interaction with science and art, where we make performances in order to create awareness for the need for cooperation and cooperation in the context of the environment, for example. And you can watch videos of science art installation on Vimeo.
I see.
Thank you so much.
Okay. Thanks so much. So yeah, thanks for giving a great talk. So actually, yeah, during your talk, there were several questions in chatting room, but I think now anyone can unmute yourself and can ask a question to the Dr. Nowak. Yeah, please. Yeah. Okay, then let me read one of the question in the chatting room while waiting. Oh, Yanis, yeah, please go ahead.
Yes, thank you, Martin, for a very stimulating and thought-provoking